All right. Good morning. Thank you for coming. So I'm going to keep my hands occupied so I can point things out and so you can all hear me. So I'm going to talk to you about planetary mapping in the digital form. It's fairly recently that digital geologic mapping has come around. Just a little bit about myself. I was born locally, Allentown, and grew up in not too far, about an hour south of here in East Greenville. I've loved nature and space and the outdoors all my life, and that's kind of directed me to where I am now. I spent all my college years in Pennsylvania. I went to Westchester for my undergraduate, and then University of Pittsburgh for my master's and my PhD. I was a postdoc down at Goddard Space Flight Center in Greenbelt, Maryland, and I've been at Planetary Science Institute, PSI, ever since. So, planetary mapping, or people's fascination with planetary bodies, goes back, thousands of years. The moon is obviously the biggest planetary object in the sky that you can see with your naked eye. So that brought a lot of fascination, obviously, with the peoples of the ancient times. So they could see that with the naked eye. They would come up with all kinds of ideas about what they're seeing. Even back then, they believed that the moon was a perfect sphere. So, that's not a new idea. No reason to go against that idea. And some people had the idea that the surface was made of glass or polished silver. They thought maybe they were seeing the reflection of the Earth's surface on the moon. So they had different ideas about what was going on. They didn't know it was an actual place on its own. But as times progressed, you had a number of scientists and astronomers and astrologers going through and starting to think about what's going on with the moon. Galileo, one of his first sketch maps, showed, by looking at the terminator, where you have the dark and the light half, the lit half of the moon was not smooth, that you had topography. There were mountains formed by craters and depressions. As telescopes got better and astronomers did a better job at sketching, the sketches come to be more like what we're familiar with as when we look at the moon and see the surface and the different features on the moon, with the dark mare and the brighter highlands, and as time progressed and again telescopes got better, they started picking out individual craters and seeing these features as actual features. And even better telescopes doing highly detailed maps or sketches of specific areas. And then this is one of the last, I keep going here. Before spacecraft data. This is one of the highest resolution photographic mosaics that we have, made with the LROC, the Lunar Reconnaissance Orbiter Camera wide-angle camera mosaic. It's about 100 meters per pixel, and that's what we use, or at least I use, for a lot of my mapping as a base map. Same thing for Mars. Although we can't see the surface with our naked eye of Mars, so we had to wait a little bit until telescopes got much better. And this is one of the first maps, sketch maps of Mars, just noting albedo differences on the surface. There's bright and dark areas. This got a little bit better as telescopes improved. The dark areas started to take shape, a little more shape. Bright areas take a little more shape too. And then we have Schiaparelli, who noticed lines all over the surface of Mars. And the Italian word for channel is canali. He thought they were channels, and he termed them canali. Well, along comes Percival Lowell, who takes that interpretation or misinterprets that translation into canals, suggesting intelligent life built these canals, and that's how we get War of the Worlds. So even misinterpretations of science, scientific things can lead to science fiction and good stories. And this is the Ebisawa, one of the last sketch maps made from telescopic observations of Mars before spacecraft. And this is the merged mosaic from Viking 1, 2, and Mars Reconnaissance Orbiter image data, and it's about 1 kilometer per pixel. So you can see those dark areas are more of the highland areas, the uplands, and the brighter areas are more of the smooth plains of Mars. Now, this is a lot of information. The point of this is to show that planetary science, at least as far as spacecraft exploration goes, didn't really start until the 60s. And once we got past Viking, there was a lull through the 80s until we get to the 90s, and exploration for the moon and Mars really ramps up. We have a lot of investment, or NASA has a lot of investment in spacecraft and exploration of these bodies with the intention of actually sending humans back. Because you had Apollo in the 70s, late 60s and early 70s, and we wanted to go back. So you wanted to collect data, lots of data. And this is just a rough list of the data sets that are associated with these spacecraft. Some of the data sets I use mostly image data, topography, and spectral data, but there's planetary scientists that do all kinds of investigations with these data. A little bit of history about digital mapping and GIS and planetary science. So in 1981, this is not a plug for ESRI, the Environmental Systems Research Institute releases their software, ArcInfo. Now, ArcInfo was initially released for uses on Earth, for like urban planning and mapping of terrestrial streams and features and geologic features on Earth. So it really didn't have a planetary a use back when it first came out. Now, 1989 was the first Geographical Information System, GIS, planetary map. In 1991, a couple years later, was actually the first call in an abstract, a Lunar and Planetary Science Conference abstract for using GIS, computer-based mapping in lunar mapping. And by the mid-90s, planetary mapping using GIS starts catching on, but very slowly. Why is that? The software is expensive, or was expensive. There was a learning curve. It was command line driven. Not that many, if you were working in city urban planning and things like that, you knew all about it. You were an expert. Everybody else had their own personal favorite software. There were other packages out there. When I actually started doing mapping digitally, it was with Illustrator. So there wasn't even a geographic component to it. It was just static line and vertices. And at the time, there wasn't much encouragement to use it because of all these issues. But in 1998, the USGS, the United States Geological Survey, picked up the cause. They saw a community that wanted to do this, myself and others, and they worked with ESRI really close to help develop planetary components for the software. And in 1999, the USGS started up their website called PIGWAD, which was at that time, a huge data repository of global mosaics of different planets, different point files with such as nomenclature for each of the planets. They started going through some of the older geologic maps and digitizing them and putting those online to make them available for everyone. So this was a good resource, going backwards, a good resource for people like me to kind of see what's out there and get an idea of what we can do. But now GIS and digital mapping is very well integrated into the community. For me, so my first mapping experience was in '96 when I started my master's. I mapped wrinkle ridges and impact craters in an area on Mars called Hesperia Planum. Did I use GIS or computers? No. I used sheets of acetate over top, some of the old NASA maps, and used Sharpies to draw out what I was doing. We at the time at Pittsburgh, we didn't have the capability yet, so we had to go old school. My first geologic map was of the Rural Valles region on Mars. Also in my master's, I used Mylar paper and pencils and a light table. So still no geologic mapping on a computer. It wasn't until towards the end of my master's that we actually had GIS classes for ArcInfo, and that was with Dr. Harbert, who was our geophysicist and ArcInfo guru. And he was a typical scientist, crazy hair, stacks of journals from floor to ceiling all over his office. He had a narrow pathway if he wanted to go get to his desk. He would go through things in the class so fast, and he'd like, what did you just do? That was really cool. Slow down. And we're still doing command line driven stuff. But when he came over to you for like some special to show you what he did, he'd say, oh, just pull up the little GUI, link there and do it the same way. It's like, why didn't you show us the easy way to begin with? But that's just the way it did. You had to go through the hard stuff to get to the easy stuff. And with GIS, ArcInfo, there's about 10 different ways to do the same thing. So it's a very, very complex bit of software, but it's very helpful and very useful for this kind of work. I did some watershed modeling. So on Earth, you want to map out where watersheds are, where streams are, because you want to know where flooding is going to occur. You want to know where houses should be placed. And so I did a similar type of thing that we do on Earth, looking at Martian valley networks. And it worked out pretty well. I did all kinds of geologic maps. I'm going to show you a few. Today we're going to look at maps of the moon, some of the lunar quadrangles, the South Pole quadrangle, and the South Pole Aitken Basin quadrangle. So you get that today. Tomorrow, if you're coming back, you get to see Mars. So I kind of split up what I'm doing, because I've done so much mapping. I have so much cool stuff to show that I gave you 2 different talks. Geologic maps. What are they? They are 4-dimensional systems that represent the distribution of different types of rock and superficial deposits, as well as the locations of features and structures. For example, impact craters. There's Tycho crater on the moon, and a bunch of other craters in the highlands. We have volcanic channels. This is a volcanic channel on the moon. We have fluvial channels, carving the surface of plains units and highland units on Mars. We have volcanic cones. So GIS is really good at building databases. So if you have a lot of these point features, you can go in and do classifications of all these little cones. This is the Marius Hills on the moon, an old volcanic center on the moon. And another type of feature on different bodies, you have fractures. This is a Floor-Occator crater on Ceres that has all this pattern of fractures. And you see this a lot in craters on the moon and Mars and Mercury. So there's similarities between different bodies. And some people look at those similarities among the different bodies to try and develop hypotheses about how these features formed and if they're similar or how different they are. Reading a geologic map is understanding not only where all these different materials are, the different colors represent different geologic units that I've identified, and knowing where the structures and features are and how they interact with each other, but how and when these features formed and what are the relationships between them. That's really the meat of what geologic mapping is. It's a puzzle, it's a mystery. You have all these things that we want to map and identify, and how do those things come together to make a coherent and realistic, geologically realistic story. And with a GIS, you get this component that they are now interactive, electronic documents, and you can put science issues into geospatial frameworks. So everything comes together in this map. You can note the size and the shape and the depth of craters, for example, or other features, the physical, the chemical contents, context of materials, and how they blend data display with the results of interpretative research. Yeah.
You use geological mapping, like we talk about whether they were or not water on various planets. Can you identify whether that's true or not?
Yes. So for example, Mars, we look at the shape of the feature. You look at the context of the feature relative to other features. So I think, well, this is the moon talk. If you come back tomorrow, there are volcanic channels on Mars, there are fluvial channels on Mars, and they look different. So you can tell the difference between the two. Fluvial channels, for example here, they form on different surfaces than some of the volcanic channels. So and the volcanic channels on Mars are also associated oftentimes with lava flows, old lava flows. So you can, yeah, yep, right. Mm-hmm. Yep, at one time Mars it had some flowing rivers. Whether or not it was sustained flow, probably not. Probably looking at short bursts or seasonal activity. Okay, so some of the data I use, again, this is the mosaic, the L-Rock WAC mosaic that I use for the base. Oftentimes, we can look at, some people look at global scale maps or regional scale maps, or you can look at a real detailed map of a feature, or make a detailed map of a feature, for example, Tycho. And at that scale, once you start getting into the surface, then you get to the L-Rock NAC, which is the narrow angle scale images. These are 1.5 meters per pixel. So you're seeing large boulders on the surface. For example, here's a volcanic old lava channel on the floor of Tycho crater. So here you're looking at the central peak. This is the oblique view of the floor. This is was all at one time molten impact melt. So some of it flowed across the surface and cooled in this. How tall? It's a mountain, yes. So that, yeah, it's probably a kilometer or two, so half a mile to a mile high.
So you showed a picture before of fractures.
Yes.
That had to do with the crater. Is that like radiating from the crater?
Those fractures, when they form inside craters, they're usually, so a crater are circular, and so they form in kind of a circular pattern normally around the crater. So that kind of tells you that stuff was hot and it's cooling, and as it cools, it cracks. Kind of like mud, if you ever had a big mud puddle, and as the mud dries out, on a hot day or something, it'll start to crack. This is topography. Topography is a huge bonus to have because we can see where the low areas are and the high areas. So this is the near side, far side, North Pole, South Pole. What I'm going to be talking to you today about is areas of mapping in this feature here, which is a South Pole Aitken impact basin, and also South Pole area. But on the near side, which is the side that faces the Earth all the time, we have ancient impact basins that are filled with maria, or basalt, old basalt lavas. So at one point, the moon, millions of years ago, the moon was volcanically active. You had these large impactors hitting the surface, heating up the surface to the point of melting. And as that melting cooled, you still had heat inside of the moon erupting more volcanic materials out onto the surface. So at one time, the moon was a dynamic planet. And here's actually a stereo DTM, digital terrain model, based on some of the WAC images. So you can make individual DTMs of a place you're interested in. There's a lot online. If you go searching for LROC WAC DTMs, you can get all kinds of different cool features to look at. Some spectral data, spectroscopic data, which show chemical and mineralogical properties. This is a Clementine, so from the early 90s data, UV, ultraviolet, and visible wavelength. That basically shows, so the reds show feldspathic, or the highland, what the rocks that make up the highlands. It's strongly showing that. The blue colors, the greenish and yellow colors show mafic materials. So this is the basalt rocks filling the large impact basins. And then the blues kind of show maturity, or how young or how fresh certain materials are. So you have craters like Tycho and this Mare unit here that are a lot bluer, so those are more fresh or fresher appearing units. You also have an iron map, derived iron, so you can see iron correlates very well with the volcanic materials, which is very similar to what we see on Earth. If you go to look at Hawaii, where basalt is the dominant volcanic type, material type, it's high in iron, it's dark in color, it's very similar to what we see on the moon. This is a hydrogen map from lunar prospector data. So you have strong hydrogen signatures at the poles. This is the North Pole and South Pole, which are good targets for sending explorers, astronauts. It would, no, not in the atmosphere. It would be under the surface or in shadowed areas. So there's some areas on the moon that don't get any sunlight at all in craters. Would be challenging to get to those areas, but those are potential areas where you could find water ice to extract for usage by astronauts. At the poles, no, because those are in craters, so it's very hard for telescopes to see in craters. So you need spacecraft data or a rover or an astronaut to get down there and start digging around. And that's hopefully the goal of Artemis, whenever that gets to the moon. So, what time we got? All right, cruising along. We're going to look at some of the mapping that I've done in the eastern South Pole Aitken Basin, LQ24, and LQ30, the South Pole. So here's LQ30 covering the South Pole, which is this one, and LQ24 is over here, which is in this map over here. I've been involved with all of the maps to some degree, with LQ29, made by a colleague, Eileen Yingst, that is in preparation. It's been through the review process once and got sent back to us, and we're revising based on their comments. So, what are the scientific objectives of looking at these quadrangles? Why do we want to map? There has to be a scientific reason of why you want to map. What is the role of volcanism on the surface? There are there is evidence of ancient volcanoes, eruptions onto the surface in these areas. What are some of the geologic materials that are exposed at the surface? And what are the ages of these geologic units? And so locations within eastern South Pole, South Pole Aitken and the South Pole have been identified as targets for human and or robotic exploration. Some of the data sets that I showed before, again, we have this is for LQ24, we have the visible base, we have the topography, we have the Clementine mineral ratio. A lot of it is very red, so very feldspathic. You got a few blue areas of basalt or mafic materials, so that really dark lavas that erupted onto the surface, which you can see in these different data sets here. Here's derived iron, as we saw before. And go back. The Apollo impact basin is this feature here. That's the largest impact basin in the area, in this quadrangle. Just a quick regional overview. So there's about 16 kilometers of relief in the South Pole area from this mountain here, Malapert Mountain, which is very close to the South Pole, the direct South Pole. And Antoniadi crater is the deepest. This is Antoniadi crater here. That has the deepest point in this quadrangle at -9 kilometers. The near side area, which is this part here, has lots of highland terrains versus the far side area, which is the very southern part of SPA, the South Pole Aitken Basin. And SPA is a 2,600 kilometer impact basin that hit the moon, and one of the oldest impact basins that we can recognize on the moon. Okay. This is the geologic map of the South Pole. So you can see a lot of the materials that I've identified are impact craters. So this yellow, the browns, these are all crater materials. If you look over at the key, the legend, the greens, the yellow shades, and the brown shades are like ejecta. So the material that was thrown out as the asteroid or the meteor hit the surface, gets ejected out, and forms this radiating pattern of material around the crater form itself. We have different plains materials in the blues and the reds and the pink. Over here, there's some blue plains, a little bit of smattering of blue plains here. And then lastly, we have a big chunk. Since I was we had good coverage of Schrödinger, this impact crater here. We did a good detailed map of that impact crater with a number of different plains units there. Now, if we look at some of these plains, these are on this side of the map. These are the dark plains. What we think of as mare material. So stuff that was erupted onto the surface, or as an impact. Some of these are in craters. So as an object hit the surface, it heated up the surface material underneath it that it hit to the point of being liquid, molten, and that and that over time cooled to form these dark deposits, dark plains. You have brighter plains material. The brighter plains, also probably a variety of molten, one-time molten material that has been mantled or covered up by other stuff. So maybe ejecta from another crater. There's this stuff called cryptomare that still confuses me, because if it's mare, but it's cryptomare in that you can see the dark signature underneath a mantle of other stuff. So whether it's, like I said, an ejecta that has dispersed a very light coating of stuff onto this dark material, it obscures the darkness of what this would be for the dark planes. And that stuff is all over the moon as well. This is an interesting feature. So this is crater Mauritius, where we don't expect to see a lot of it's a small crater. You don't expect to see a lot of constructional or volcanic activity. This is a little conical feature. So it might have gotten hot enough in this crater, or at least underneath the crater in the subsurface, where you had some molten material, and then over time that might have erupted onto the surface and made this little cone. This is the only one that I've noticed in this crater, or even in most of the craters on the south side, south pole area of the moon. So it's not that common in craters of this size. This is fairly small, like on the order of 20 kilometers or so. Oop. Yeah. This is Schrödinger, as I pointed out before. Schrödinger is about 320 kilometers or 200 miles across, with a depth of about 3 miles or 4.8 kilometers from rim to floor. This is one of the larger craters. It does show really good evidence for post-formation volcanic activity. And you can also see these lines here, and the red and the blue and the yellow. These are secondary craters from other impacts. So the red is from Oriental impact, the blue is from Antodiadi, which is here in the south pole area, and the yellow is from Humboldt impact crater. So these other craters hit the surface of the moon, sent material flying, even large chunks of rock that then impacted the surface. And so secondary craters are like pollution. So when we look at the surface, we want to, since we can't go there every day and test the surface, we want to know how old the surface is. And one way we do that is by counting impact craters on the surface. The more impact craters you have on a surface, the older it is, because it's been exposed to space a lot longer and it can accumulate more craters. The fewer craters a surface has, a geologic unit a surface has, the younger it is, because it hasn't been exposed to impacts as long. So then when you have these secondary craters, that just screws everything up, because you got to filter through and pick out really carefully which are the secondary craters so you don't mess with your statistics. If you start counting secondary craters, then that artificially makes the surface older. We want to try and be as accurate as we can and eliminate as many of this pollution secondary craters as possible. And I want to point out that Schrödinger has been identified as a target site for the Commercial Lunar Payload Services, CLPS, 12 lander, which is going to have a far-side seismic suite. So looking at the structure of the subsurface underneath Schrödinger, the lunar interior temperature and materials suite, so testing the thermal regime, how hot it is underneath Schrödinger, and this lunar surface electromagnetic experiment. So hopefully that will land, and that's the artist's conception of the spacecraft. And this is the closer up map of Schrödinger impact crater. So these red and oranges are what we identified as actual volcanic materials that erupted onto the surface. The shades of green are different plains units that have different qualities, different physical appearances. Some are knobby, some are smooth, some are hummocky. And those are the basic descriptors that we use to separate out different geologic units that we can identify. Just, does this unit have knobs? Yes. Does this unit have knobs? No. Are they different? Probably. Is there anything else we can tell about them? Well, they might have a different albedo, so that one might be brighter versus darker, so we can use that. So we can use brightness. And so it's very, the way we go about mapping is fun and interesting how we pick out things. Just also texture. So this is a part of the inner peak ring of Schrodinger. The texture has this what's being called elephant skin or tree bark. So if you picture a close-up of an elephant and look at its skin, that's the kind of feature we get here. If we look at some of these base and floor materials, this is the some rugged plains, so it's kind of chewed up with older impact craters, small impact craters, bumps and lumps and holes all over it, versus the hummocky plains here, which is a lot smoother. You don't have all these impact craters. You have some small ones, but they're really well defined. And all these different shadings, let me change my batteries. All the different shadings are where hills are, so there's hummocks. One way we use to identify. Now this is interesting. This is the knobby plains. So here we have an impact crater. This was mapped as impact crater material. So this is ejecta around this crater. We have a similar texture here, which we called knobby plains. So putting two and two together, we notice there's this Ganswint crater just outside of Schrodinger, just on the rim of Schrodinger. What we did is interpret this ISKP, this knobby plains, as impact ejecta from Ganswint. And we can't make a direct connection between the two because we lose it in the rim of Schrodinger, but we can interpret it as impact ejecta. And a lot of times you don't have these one-to-one connections. You don't have one feature connecting to another feature or a unit connecting to another unit. But if you have spatial relationships, you can make those speculative interpretations. And it's up to other scientists to go in and say, I question that, I'm going to test that, and either support your interpretation or not. Also in Schrodinger, as I pointed out in other areas, we do have lots of fractures on Schrodinger. Now some of these fractures do not radiate or are not oriented in a circular pattern around the crater. They're more all over the place. So you have some cutting across the crater, some more like spokes going from the center of the crater out towards the outside. So what that tells us is we had molten rock, molten material in Schrodinger, and it's been cooling. It has cooled over time, fracturing the surface. This is a cinder cone. This is an eruptive location. This is not an impact crater. That's a small caldera where material was ejected out. And so this is what a cinder cone is where you have explosive eruptions, and you have ash and glass, volcanic glass being erupted onto the surface. There's no atmosphere on the moon, so it can go a little bit farther. This material can travel a little bit farther. You do have evidence for some effusive or lava flow material that is on the surface in Schrodinger. So this is, I hope you can see that. This is a Clementine image. So from the 90s, a Clementine image of an old lava channel that hadn't been identified until we did this mapping. And luckily we are able to have, this is a NAC image, one of those high resolution. This is 500 meters for scale. So really nice, crisp, clear view of this meandering ancient lava flow channel on the surface of Schrodinger Basin. And just the cinder cone here, this is a picture of Earth, very similar, where you have eruptive material that's explosively depositing material around it, forming this cone. So this would have been a cool place to sit and watch a few 100,000 years ago.
Does anyone have pictures of active
On the moon, there is no active volcanic activity today. It is pretty much dead inside. There's very little heat. The only heating you might get is from an impact that hits the surface and just warms up where it hits. But yeah, there's no active volcanic.
So is there any theory of how it was able to happen in the past, but it doesn't happen now?
In the past, well, as the moon, the going theory for how the moon formed is that it was an impact, an object hit the Earth, threw off a bunch of stuff around the Earth that came together to form the moon. That process would have left a lot of heat, involved a lot of heating as it came together, and the moon would have been pretty much molten for quite a long time. As the moon cooled, you had some rocks forming highlands, the bright areas that we see, other rocks forming the dark areas of the moon that we see. So during that time, and at the same time, you have other impacts hitting the moon, forming what we see today when we look at the moon, the dark areas, the mare. So that's the best evidence that we have that the moon was volcanically active. And there are some really clear, as I showed you, have that one with the picture with all the little colored dots, red, blue, and green dots, showing all the different cones. There's areas like that all over the moon. You can see lava flows. You can see volcanoes, volcanic cones like we could see. So there's a lot of evidence for volcanism on the moon. I'm going to skip that. This is the map of LQ-24. My time is almost up. So we see similar things, and the color scheme is try to keep basically the same. We have red and blues and oranges as our plains materials. So the red usually signifies, and the orange usually signifies some kind of volcanic type of plains. Well, there is only volcanic type of plains. It's not like Mars where we have wind-eroded plains and fluvial plains. Just different plains showing different degrees of I guess, stages of volcanism, where the blues are more of this cryptomare type of material. The pink and the purple, again, are more of this highlands, and this brown unit up here is the ancient highlands, and a lot of crater materials. The base, again, is the rock whack base. We got deep, dark and smooth surfaces that form the mare or impact melts, and then moderately dark and smooth surfaces that form these cryptomare. Things that we think are mare, like down in here, that are probably mare or impact belt, but we don't see any evidence. Again, the derived iron map, these nice red areas are high in iron, and they correlate very well with the dark areas on the image. And so chemistry, although we're not necessarily mapping chemistry, we can use chemical components as a descriptor in our map unit characterization. Now, this is a close-up of the Apollo Basin. This is a wax scale that we're looking at dark smooth plains 1. And I want to zoom in here on this little red box where we see these little mesas. Now, this isn't necessarily moon shattering, but what this kind of signifies, there's not many ways you're going to get this, features like this on the moon, except through volcanic activity. So what we think is happening here, this is a positive relief feature. Sometimes our eyes play tricks on us, so the sun is over here, shining its light this way. This is a raised, brightly lit face, and here's the darker face, shadowed face over on that side. There's some cracks, fractures on the surface of this feature. And so whether or not, this is probably some kind of volcanically erupted volcano, basically, or kind of a very thick eruption of lava. And there's not too many of that identified, that we were able to identify in this map area. Bright smooth plains, again, that blue. In Oppenheimer, there's some bright smooth plains over here, some of the darker plains here, and some of the really dark smooth plains in that crater. If we look at this red box here, where we have an actual, hey, look at that, a contact between those dark smooth plains and what we think are bright smooth plains, but there's a lot of stuff. There's a lot of little craters all over those plains. And hopefully you can see there is, for the most part, there's an edge. And that's what we do. We stare at images for hours and try and pick out edges. And sometimes you get lost. You step away, your eyes get buggy. You got to step away for a while and then come back and look at more images. But so texture is a huge component in helping us identify different geologic units. Okay. This is the 3 maps put together. Ideally, they'll be published individually. So this is LQ24 and LQ30, the South Pole map. Just closing remarks. Digital geologic mapping it's here, it's now. It allows us to map more efficiently and a lot faster than with Mylar paper and a pencil. The use of GIS packages software enables us to do lots of really cool statistical analyses of what we're mapping, of the surface, of the different features, things that you can't even think of, comparing different features. Making global databases of features. There are people that made global databases of fractures and valleys and channels and craters. And these geologic mapping and different analyses increase our understanding of planetary surface modification, interior dynamics, histories and sequences of geologic events. And just my little plug here, planetary research needs your help. Exploration gets lots of money. It's fun to send spacecraft, to think of new spacecraft and get lots more data and things to do. But when they send back those terabytes of data, they need people like me and my colleagues to analyze that data. So rather than having it sit, on a server somewhere, you want to have people actually using the data. And people like you, going to their computers and seeing what really cool images are out there. You could spend hours looking at high resolution images and seeing what the surface looks like of these planets. So if you're the kind of person that talks to your congressperson, tell them to support research, planetary research. Thank you. A couple minutes for questions.
A couple of questions, yeah, and then we'll. Oh yes,
yeah.
let me get the lights.
Yeah. Top button. Okay.
Any questions?
Yeah.
I guess so, in all the research we've done, I guess you can confirm there's no cheese on the moon?
No trees.
No, seriously, but, no,
Or cheese.
I
Yeah.
actually have a question. So I think we only get to see one side of the moon, right?
Correct.
Is there a reason why?
Can you repeat the question?
Yeah. So he asked why we only see one side of the moon. So over millions of years since the moon formed, at one time it was rotating, but its location, its distance from us, and the gravity of the moon and the gravity of the Earth locked it in that position. So it slowly over time, the rotation of the moon slowed down to the point where we don't visibly seeing it rotate. As it goes around,
It's rotating.
right, it's rotating, but it's weird to think of it, but it's
Kind of like global.
yeah, exactly, yes. Yep. Yep. Yes.
You're talking about staring at these maps and trying to pick out
Mhm.
pictures and stuff like that. Will you be able to use AI to be able to help with that?
Ever since I got into the field even as a grad student, There have been people coming up with ways to automatically identify, like impact craters are the big thing because they're everywhere. They're important features. And there have been studies for years about what's the best, way to go about doing it. I don't necessarily trust it myself. It's not fun to sit there and count and measure thousands of craters. But I've also looked at some of the computer-counted crater data, and it's like, well, that's not a crater. I still have to go through and manually say, that's wrong, that's wrong, that's wrong, or you missed that one. So it's good and it's bad. It has its pluses, it has its flaws. And you gotta, depends on the type of person you are, if you want to do it yourself or trust a computer. Yep.
If I understood you correctly,
Oh,
the craters on the dark side of the moon,
mhm.
you suspect they have water in there, but you can't really actually figure that out yet. They were just sent spacecraft with bright lights and then you can do spectral analysis?
At the far side, or I mean not the far side, the South Pole. Yeah, so once you get out of the polar regions, the hydrogen, there's very little hydrogen because you have the solar wind and that just goes off into space. But at the poles, where you have these permanently shadowed areas, that's where water molecules can get trapped and stay because they're not going to have the solar heating to escape back out into space. And so over time, you get the buildup of, hopefully, deposits of ice or ice.
The whole cool
But-
part, can't we just,
Yeah.
I mean,
Oh, yeah.
basically, we're close enough to just shine a flashlight on there.
Oh, there's spacecraft, yeah, that look for it's a GRS, a gamma ray spectrometer that picks up the hydrogen atoms, and that's the one that really,
Okay.
yeah, that's the instrument that really picked up where the hydrogen and got people thinking this is a resource that could be used at the South Pole, mostly the South Pole. There's a little bit at the North Pole. But there's a lot more craters at the South Pole, bigger with more shadowed areas. Any more questions? No? Thank you.
Thank you all for coming. Thank you to Dr. Scott Mest.